Part 107 weather regulations require a minimum flight visibility of 3 statute miles from the control station and a minimum distance from clouds of 500 feet below and 2,000 feet horizontally. Operators must ensure a safe aircraft and understand how temperature, dew point, and density altitude affect performance. Weather is one of the most test-heavy sections of the Part 107 Remote Pilot Knowledge Exam. It is expected that the following areas are understood. Weather theory. Sources of aviation weather data. Microbursts, wind shear, and stability. Cloud types and their associated hazards. Atmospheric pressure, density altitude, and performance impacts. And interpreting METARs and TAFs. Weather is driven by many factors. The first is temperature. Uneven heating causes the movement of air leading to wind and convection. It is important to remember that warm air rises and cold air sinks. Another factor is the dew point. The dew point is the temperature at which air must be cooled to be fully saturated, also known as 100% relative humidity, and begins to release water vapor or condensation. High dew points indicate high moisture content, which can fuel cloud development, fog, and severe storms. Temperature inversion is another weather factor to understand. A temperature inversion, or weather inversion, occurs when a layer of warm air settles over a colder air layer near the ground, reversing the normal atmospheric trend where temperatures decrease with height. Atmospheric pressure is another aspect that can affect drone operations. High-pressure areas provide stable air and clear skies, while low-pressure areas lead to unstable air, clouds, and precipitation. Humidity affects the density of air. The more moisture, the less visibility, and the increased possibility of clouds and precipitation. These factors affect the stability of the air. When air is stable, it will allow for smooth flights, but poor visibility and steady precipitation. An unable stable air leads in increased turbulence, good visibility, and thunderstorms. While there are many types of clouds, there are only a few that will be required to be known for the Part 107 exam. The first is the cumulonimbus, sometimes referred to as CB. These are the most dangerous clouds for drone operations. Cumulonimbus are associated with thunderstorms, heavy rain, hail, lightning, microbursts, and extreme turbulence. Another type is stratus clouds. They typically have low, widespread stable air, so they can reduce visibility significantly, affecting the decision to fly or not fly. Clouds and other air elements can lead to thunderstorms. A thunderstorm is a, generally short-lived, convective storm produced by cumulonimbus clouds that always contains lightning and thunder. They require moisture, unstable air, and lifting action in the atmosphere. It must be noted that a drone should never be operated in a thunderstorm. There are 3 stages to the formation of cumulonimbus clouds. The first is the towering cumulus or building stage. Here warm, moist air rises, condensing into a towering cumulus cloud. There is little to no rain, with occasional lightning and rapid vertical growth. The second is the mature stage. This is the most dangerous stage due to the coexistence of updrafts and downdrafts at the same time. Precipitation begins to fall, creating a downward rush of air. It can feature heavy rain, frequent lightning, hail, strong winds, and potential tornadoes. And the dissipating stage. Here the downdraft overcomes the updraft, cutting off the supply of warm, moist air. Then the storm weakens, precipitation tapers off, and the cloud begins to dissipate from the bottom up. One thing that may be asked during the Part 107 exam is height of clouds based on relevant information. You will be given information such as an air surface temperature of 70 degrees and a dew point of 48 degrees at a field elevation of 1,000 feet MSL. To calculate cloud height, first find the spread between the temperature and the dew point. Next divide the spread by a constant of 4.4 and multiply by 1,000. And lastly convert to MSL by adding the field elevation. For the example, the dew point of 48 is subtracted from the temperature of 70 degrees, giving us 22. Then the 22 is divided by 4.4, resulting in 5, which is then multiplied by 1,000 equaling 5,000 feet. Then the field elevation is added to the 5,000, giving us a cloud height base of 6,000 feet. One weather condition that a drone pilot must understand and be aware of is a microburst. A microburst is a highly localized, intense column of sinking air, or downdraft, within a thunderstorm, less than 2.5 miles in scale, that produces damaging, straight-line winds up to 150 miles per hour. They are a severe downdraft that hits the ground and spreads out. The downdrafts can fall at a rate of 6,000 feet per minute, so there is significant force, making them the strongest hazard to a drone flight. Wind shear is another hazard to drone flights. It is a sudden change in wind speed, wind direction, or both. They are often found near thunderstorms, during temperature inversions, near terrain, and in microbursts. Because drone pilots must maintain a visual line of sight, fog can hinder the ability or authority to fly in fog. Fog presents a significant safety risk to the aircraft. The types of fog include radiation fog, which is a common, often dense, low-lying cloud formed overnight when clear skies and calm winds allow the ground to radiate heat into space, chilling the air near the surface to its dew point. It typically develops in valleys, near water, or during winter, often dissipating after sunrise. Advection fog forms when warm, moist air moves horizontally, advection, over a cold surface, causing the air to cool from below to its dew point and condense into fog. Unlike radiation fog, it can persist for days and form under cloudy skies with moderate winds. It is common along coastlines and over snow-covered ground. Upslope fog is a type of fog that forms when moist, stable air is forced upward along sloping terrain, such as a mountain or hill. As the air ascends, it cools adiabatically to its dew point, causing condensation and creating thick fog that can persist as long as the wind blows. Steam fog or evaporation fog or sea smoke is a shallow, low-lying fog that forms when very cold air moves over warmer water, causing the water to evaporate and immediately condense. It resembles wisps of steam or smoke rising from lakes, rivers, or polar seas. It requires a significant temperature contrast to occur, typically during cold, clear autumn or winter mornings. An ice fog is a type of dense, surface-level fog composed of tiny suspended ice crystals rather than water droplets, forming only in extremely cold, calm conditions, typically below -30 degrees Celsius or 22 degrees Fahrenheit. Drones fly by the blades pushing against the air in the atmosphere, creating lift. So the thickness of the air plays an important factor on performance. Air density is the mass of air per unit volume representing how closely air molecules are packed together. It is not constant. High density altitude results in thin air, and therefore poor drone performance. Low density altitude provides thicker higher and higher drone performance. The factors that affect density altitude are temperature, humidity, and air pressure. The impacts on the drone include poorer battery performance, less lift, and the effectiveness of the drone cooling. To calculate density altitude, first pressure altitude must be calculated. This is done by subtracting the current barometric pressure from the standard pressure and multiplying it by 1,000. The standard pressure used is always 29.92. Then add the field elevation to come up with the pressure altitude. Then to calculate the density altitude, take the field elevation and multiply it by 0.002. And then add that to 15 degrees Celsius. Next subtract the current actual temperature from the result of the previous step, and multiply by 120. Finally add the result of this process to the pressure altitude to get the density altitude. Here is an example. The current barometric pressure is 28.90 and the actual altitude is 1,500 feet. So following the formula, subtracting 28.90 from 29.92 and multiplying by 1,000 gives us 1,020. And we add that to the 1,500 elevation, equaling 2,520. Then to calculate the density altitude, we take the 1,500 field elevation and multiply it by 0.002, giving us 3. The 3 is added to 15, making it 18. If the current temp is 24 degrees, we subtract 18 from 24 and multiplying that 6 by 120 for 720, which is then added to the pressure altitude of 2,520 for 3,240. Therefore, the pressure altitude at 1,500 feet with a current pressure of 28.90 and a temperature of 24 degrees Celsius will act like an air density altitude that would be seen at 3,240. As a drone pilot, it will be beneficial to understand front systems and their effects on the aircraft. Cold fronts are fast-moving, often include thunderstorms, produce higher turbulence, and result in rapid weather changes. Versus warm fronts, which are slow-moving, may include steady precipitation, and can have low clouds and poor visibility. The last weather consideration for drone flights is icing because they are extremely vulnerable to icing. It is the result of visible moisture and freezing temperatures. The effects of icing are added weight due to the weight of the frozen water built on the aircraft, reduced lift because of the added weight and moisture in the air, and disruption of sensors. The last section of weather-related topics to cover are the METAR and TAF. METAR stands for Meteorological Aerodrome Reports. They are standardized hourly aviation weather reports providing crucial, real-time surface observations at airports. Used primarily by pilots and meteorologists, these coded reports detail wind, visibility, runway range, weather phenomena, clouds, temperature, dew point, and barometric pressure. Here is an example of a METAR. The first thing you can see is the type of report and the station the report covers. Here it is the JFK Airport in New York City. Next is a date and time of the report. It is important to note that the time is reported in the Zulu time zone, which is the Greenwich Mean Time, or GMT, meaning the time in Greenwich, England. Wind direction and speed is represented next. The first three numbers are the wind direction, here it is 180 degrees. And the speed is the fourth and fifth number, followed by KT or knots. This is followed by current visibility. This report shows 10 sm for statute miles. Next you will find the cloud heights min and max levels. The first block shows few clouds at 2,000 feet and scattered clouds at 25,000 feet. Then the current temperature and dew point is provided. On METARs, the temperature is given in Celsius. Lastly, the altimeter or barometric pressure reading is provided in inches of mercury or Hg. A TAF stands for Terminal Aerodrome Forecast. It is a coded meteorological report issued 4 to 6 times daily, predicting weather conditions, such as wind, visibility, clouds, and precipitation, within a 5 statute mile radius of an airport for a 24 to 30-hour period. Below is an example of a TAF that will be explained in more detail on the next slide. The first two down blocks are the type of report and the station, which here is KGSO, or Greensboro, North Carolina. The next block is the forecast time, with the first two digits being the date of the month, and the last four numbers are the time in the Zulu time zone. Next provides the date and hour the report validity starts and ends. The first two digits is the day of the month, and the last two digits is the hour, followed by a slash and another date and time. This is followed by the wind speed, here variable at 4 knots. And visibility in statute miles. The P before the 6 stands for plus, so it's more than 6 statute miles. Then there is precipitation and cloud cover. Here showers in the vicinity, with scattered clouds at 4,500 feet and broken clouds at 12 and 25,000 feet. The lines below the top line show expected changes throughout the life of the report. The FM means from, so FM 060300 is from the 6th day of the month at 0300. The winds will be at 220 degrees and 3 knots. Visibility will still be at plus 6 miles. With scattered clouds at 6,000 feet. And broken clouds remaining at 12 and 25,000 feet. Here is a table of acronyms and qualifiers you may find on a METAR or TAF. It will be beneficial to familiarize yourself with these because you will be asked to read METARs and TAFs on the Part 107 exam. Understanding weather and its impacts on flying drone is important for safe operation and required knowledge for the Part 107 Knowledge Assessment. Thank you for watching this video. Please hit the subscribe button to access additional FSTG videos.